Good afternoon, everyone. It's my great honor to present two talks in this session. They're both going to be live streamed, and they are addressing the software ecosystem for HPC. So our first talk is by Lois Curfman McInnes. Lois is an Argonne Distinguished Fellow, and she's Deputy Director of Software Technology for the US DOE Exascale Computing project. She received the 2015 SCIM-ACM Prize in Computational Science and Engineering, a 2009 R&D 100 Award as part of the PETSI team, and the E.O. Lawrence Award in 2011 for outstanding contributions in R&D supporting DOE and its missions. Lois is a SCIM Fellow and serves on the SCIM Council. So please join me in welcoming Lois McInnes.
I'm truly honored to be here and to speak with the HPC community. I wish I could be there in person, but in the absence of that, I'm delighted to be here online. Today, I am eager to talk about work that's ongoing in the community to work toward high-performance scientific software ecosystems. What's very exciting at supercomputing in particular is this year's theme, Science and Beyond, where we are focusing on the wonderful achievements that are taking place in high-performance computing that are bringing to bear advances across scientific discovery in areas such as energy, materials, chemistry, and many more. This slide shows work underway within the Department of Energy's Exascale Computing project, focusing on a variety of applications. We as a high-performance computing community typically focus on scientific advances and often on also advances in new computing architectures, in math and computer science, such as new algorithms and new ways of understanding advances that leverage new architectures. What we don't always focus on so much is the critical role that high-quality scientific software plays in these advances. So today, I want to focus on just that topic. That is the critical roles of scientific software ecosystems and also communities of people who are working to develop those ecosystems. And in addition, the role that each of us in the community can play to help that software in those communities to thrive. This slide shows a quote by author Ann Patchett. As I was considering how to approach this topic, speaking today, I happened to be listening to an Audible book by Ann Patchett. And although she was speaking toward a different topic, the point that she made, I believe, really resonates for any topic that is complex, such as this one. And that is, there are many layers that contribute to understanding the topic overall, and each one of us can tell only one version of a very complicated story. So today, my focus is to consider scientific software. We now have broad recognition that scientific software is the foundation of sustained collaboration and encapsulation of expertise in high-performance computing. This slide shows a diagram that was created by the SCIM activity group on computational science and engineering, showing the way that software helps to enable encapsulation of expertise across the various areas of scientific computing, including simulation, modeling, analysis, optimization, design, and more. So this is a fun part for audience participation. So this is a chance to get a little exercise. So whether you're at home online or on site, I'd like to ask you to consider your own roles and relationships to scientific software. And when you see an answer that or a topic that resonates with you, raise your hand, or at least think about this. So first of all, do you develop software, either that you use yourself or that you provide to others, perhaps in your own research group or in the broader community? Do you perhaps use software developed by others in your work? Do you contribute to teams who develop and use software. There are many important roles in contributing to software beyond writing code. So I know many important elements of contributions include strategy, planning, logistics, raising funding. Do you lead projects or organizations or teams develop and use high-performance computing software? Are you perhaps a stakeholder or a supporter of projects that develop and use software? And finally, last but certainly by no means least, I hope we are all fans of high-performance computing software. In any case, so keep in mind these different relationships that we all have. Now let's consider the context of scientific software ecosystems, where an ecosystem, in the generalist of senses, is a group of independent but interrelated elements that comprise a unified whole. The relationships among the members of the ecosystem and their diversity are, in fact, what enables the ecosystem to function and, in some cases, to thrive. Shown on this slide are examples from the human body's gut bacteria and also Australia's Great Barrier Reef. My focus today will be to talk about how each of us can contribute towards creating high-quality scientific software ecosystems and communities. We'll talk about complex challenges, opportunities to engage, and also some work that's underway within the Department of Energy's ECP project. Shown on this slide is a link to an article that the focus area leads of the ECP project recently wrote, and this summarizes some of these points. I'd like to thank all of my collaborators and teams who I'm working with not only now, but who I've worked with throughout many years. Their work is certainly represented here, and I am honored to speak on behalf of the contributions of many, many people. I especially thank the sponsors of the Department of Energy who are funding the Exascale Computing project, and all of the staff who are contributing to the ECP project. We especially thank the ECP Director, Doug Cothey, and Deputy Director, Lori Dyson, for fostering a really wonderful community for us to do this work. Briefly, the Exascale Computing project is one thrust within the Department of Energy's Exascale Computing initiative. This is an initiative to accelerate R&D across our ecosystem and create a thriving set of advances in science using new architectures. This has been a multi-year endeavor starting in 2016, incorporating leadership among 6 labs as shown on this slide, as well as contributions throughout the DOE lab complex and from many collaborating universities. There are more than 80 amazing R&D teams working across applications, software, hardware, and infrastructure, and over 1,000 researchers. Our work is organized according to 3 focus areas, with work on applications development, focusing on driving ahead scientific discovery in 24 distinct application teams, as well as 6 co-design centers who are looking at developing computational motifs and functionality for those motifs that support applications. The second area, software technology, where I am working with teams to develop 70 unique software products that are supporting these applications, and also complementary work on hardware and integration, where we're looking at delivery of these software products and applications so that they can run on the latest new advances in machines. This slide shows a bit more detail about the breadth of the applications that ECP teams are pursuing across many, many areas. I encourage those of you who are interested to go to the ECP website and learn much more about the wonderful science advances that are underway. I don't have time to discuss those in detail right now, but I will say that the teams are very excited across the entire ECP community to be working toward the newest machines shown on this slide toward the right, Frontier and Aurora, and later El Capitan, that are in the process of coming online soon. And already our teams are working with early hardware to showcase advances in technologies that are taking advantage of these new heterogeneous architectures. In all of the new work that we're doing, we're focusing on heterogeneous accelerated node computing. This diagram, which Andrew Seeger developed, it is a nice representation about how our work as a community has been progressing over time to transition from when we primarily worked on just CPUs to when we began to get some experience with GPUs to what we're doing now, shown on the right side of this diagram, where we're working very hard to have effective, efficient, robust, and scalable performance on diverse CPU and multi-GPU architectures. So this has been a really exciting time of transition for our teams. While addressing those challenges, our community across the whole international HPC space are beginning to tackle new opportunities that are becoming possible only because of this dramatic advance in computing power. So we're working together to tackle problems that are beyond what traditionally we have done in interpretive simulations and are working toward predictive science. We're working on applications that are multi-component, multi-physics, multi-scale, increasingly incorporating sensitivities, numerical optimization, quantification of uncertainties, as well as coupling simulations with data analytics, learning, and AI. Moreover, teams are now beginning to explore complex workflows that incorporate not only simulation, but also input of data and analysis from scientific or observational facilities. This slide here is taken from a recent presentation by Ben Brown, who is leading the thinking in the facilities community about how we're moving forward to fully leverage the breadth of computing facilities and non-compute facilities in the Department of Energy. So these challenges are bringing forth many well-known elements of work that are needed. Shown on the right side of this slide is a list of scientific software challenges that Dan Katz shared in a presentation a few years ago. And it's a nice summary of the intertwined technical and sociological challenges that we're all facing for scientific software. On the left side of this diagram, we see that these challenges are magnified considerably as we increase in the scale of the problems that we're tackling and their complexity, as we increase in the size of the teams and work in collaborating teams rather than single teams, and as we increase in the lifetime of our software, having the expectation that our software works for many, many years, sometimes decades. So these challenges are both technical, especially in a research context where all parts of the cycle are being changing and our requirements are changing. The software is very complicated and messy. At the same time, there's sociological challenges, including competing priorities, limited resources, some of the challenges of interdisciplinary interactions given different perceptions of benefit and priorities. And oftentimes we get into a circumstance where we accrue so-called technical debt. This is a term that refers to the implied cost of additional rework that is required because initially a limited or less long-term solution is chosen for some work rather than instead choosing an approach that would be a better long-term solution but would actually take longer to do. So as a community, we struggle with this. And there are many organizations who over the last decade, especially the last 5 years, throughout the international community are working very hard to address these complicated problems. I would encourage you to take a look at the work by these various groups. One point I neglected to mention when I started talking is that my slides are available through a bit.ly link, and that bit.ly link was on my very first slide. So at some point, perhaps somebody could post that in the chat so that if people would like to have easy hyperlinked pointers to these organizations, they're available through the PDF of these slides. I would just like to call out the Research Software Alliance, an international group who is endeavoring to help coordinate among these various groups. So there are many more organizations worldwide. I just listed a few here, and I would like to especially call out the international work that's progressing in research software engineering. There was a wonderful workshop that took place on Monday focusing on that. I encourage people to take a look at the work that research software engineers are doing and what's moving forward in our world. Now, after we've introduced these many challenges, I'll speak about how in the Exascale Computing project, we're working to build a software ecosystem for extreme scale computing. And at the same time, we're doing that while advancing scientific productivity through focusing on improving our software and in developing a culture where we're constantly working to improve our software. This slide shows how we're working in ECP across applications, software technologies, and hardware integration. That is our three focus areas, where at the same time we're advancing capabilities in science and software, and at the same time having cross-cutting work to advance the productivity of our teams and the sustainability of our software. So we're recognizing, of course, that changing processes to have more effective software development doesn't come for free. This diagram on the left shows that in order to change what we're doing in some way, to invest in, for example, changing the way we handle version control or testing, time is required to do that. But we're finding that by investing time in making those changes, what we're able to do is to help ECP teams overall to be more effective, to spend less time and less resources to achieve better quality software, more effective science, and for us to have more confidence in the science that we're generating and the software technologies that underlie and power those scientific advances. So this really gets to the heart of working as a community to change culture. This slide is showcasing just 5 applications within the ECP application portfolio. Recall we talked about there are actually 24 applications and 6 co-design centers. Here, just for illustrative purposes, I'm showing the needs for 5 of them for wind plant efficiency simulation, subsurface flow modeling, high fidelity fusion energy modeling, cosmological simulations, and also multiphysics modeling for high energy density physics. So just these 5 applications, which are, again, only a subset of the full suite that we're considering, use and build on a variety of software technology products within ECP. This slide shows the software technology products across a variety of different applications, these 5 applications that are either being used or being considered. And so this slide makes the point that our applications are relying on multiple software technologies, and some products contribute to multiple components within a given multiphysics application. And so we really do need to think carefully and work in a concerted, coordinated way to have consistency across the software stack. So this is where the work by the ECP software technology community comes into play. Our software technology teams are collaborating together to build a comprehensive software stack that delivers robust products as needed by these driving applications. And we're focusing on areas that complement what vendors and facilities already are doing. The ECP software technology teams are working across 6 topical technical areas shown on this slide and led by remarkably wonderful people. I must emphasize that everyone within the whole ECP project has been doing such exceptional work in terms of pushing the boundaries of new creative thinking on applications, software, data structures, and collaborating across teams. And so we're really grateful for the work that everyone is doing. This slide shows that we're working across technical areas in software technology, including programming models and runtimes. tools to help with software development, tools including analysis tools, performance help, and whatnot, math libraries, tools for data and visualization, as well as work towards creating a software ecosystem means of accessing these complementary capabilities. And we're also incorporating functionality that is coming from the NNSA portfolio, but yet is being used by our broader open science community. Now, there's no way that I expect anyone to consider the details of this slide, but I would like to just point out that we're having a broad range of software teams who are working to develop 70 distinct software products and working across many collaborating labs and universities. So we're very, very happy to have such distinguished members of the HPC community as part of our project. And in fact, many of these teams have been presenting the latest and greatest details of their work here at Supercomputing as part of presentations, BOFs, tutorials, and other events. This slide shows just one example of a few highlights that are underway by just 3 of our teams. There are many, many more advances being pursued by the teams. And what I will talk about in a moment is how what's incredibly exciting and new for us is that all of these advances are becoming readily available through E4S, our scientific software stack. So when you have a chance, I encourage you to take a closer look at these advances across scalable solvers, where we're speeding up algorithms on new architectures, compression, where we're helping to manage scalable volumes of data, and also performance monitoring, where we're exploring the details of how codes are actually performing on new architectures. This slide introduces the concept of work on software development kits. Software development kits are a way for a community of projects who are developing complementary products of similar functionality can get together to determine what approaches might be prudent for them and helpful for them in order to coordinate and collaborate more effectively. The math libraries community first began working on the XSDK, or Extreme Scale Scientific Software Development Kit, in 2014 before ECP began. And they've been building on layers of collaboration that have been very successful. Currently, the XSDK just this week released the 0.7 version that shows the coordinated collaboration among all the libraries shown in the left-hand side gray box. This work is led by Ulrika Yang from Livermore, and our release across all of these coordinated software math libraries is led by Satish Balay of Argonne. The diagram in the middle shows how in each of these libraries, teams are working toward advances in functionality and algorithms, data structures, and also software interoperability in order to serve the needs of the motivating applications and work toward more effective predictive science. This slide shows the multi-layer collaborative approach that we're taking in ECP, where we're building beyond the traditional approach of individual developers of individual products. We're taking this approach of considering complementary functionalities across our different areas of software technology in a software development kit philosophy. And then on top of that, we're building the extreme scale scientific software stack, or E4S. So this is a great one-slide overview of E4S and provides an example of how we're coordinating across the community by working hard to develop community policies, common approaches to documentation, curation, and then deployment and distribution of functionality so that the tools are readily available for application teams and others. Just like to emphasize that E4S is an open software architecture, an open stack, and we welcome contributions from any teams who are interested in participating, regardless of your funding source. And I'll just mention that the stack includes contributions from a variety of work that's focused on AI and learning, as well as the more work that I talked about within ECP. So a unique element of this ecosystem functionality is bringing together communities of people who develop software to determine what makes sense for them to collaborate. And we reflect this work and this dialogue by establishing community policies. Shown here, the very first version of community policies for E4S. This work has been led by Jim Willenbring, who's coordinating all of the software development kits across topical areas. So we don't have time to discuss these in detail, but let's just encourage people who are interested, when you have a chance, to please take a look at the current policies and think about whether you have feedback. Certainly the E4S community welcomes input and feedback from everyone whenever you have time for that. And I'll just mention that we found it incredibly valuable as a community to work on coordinated approaches to teams specifying how they're handling these various topics in testing, documentation, error handling, and whatnot. So we're not requiring a single approach, but we're requiring that teams address these topics and communicate about how they're addressing these topics. This work has enabled us to coordinate as a community in order to serve the needs of application teams. Shown on this slide is just one example from our collaborators in Fusion, who are doing whole device modeling of fusion energy, where they are able to use a build cache, a E4S SPAC build cache, that is enabling them to speed up their work in compiling and building new applications. So they've spilled up their time for building by over a factor of 10, which is really having a profound effect on their productivity during their work each day. Likewise, we've had similar advances in productivity for the ExaWind project, who are working on wind plant modeling. So in summary, E4S is an open architecture. It's an attempt to deliver high-quality, reusable products in a collaborative way. It is open, and it is certainly a place where we welcome contributions. So this is not a commercial product. It's not something that requires using all elements of the E4S. What is intended is that individual applications or users can pick and choose the parts of it that would be relevant for their needs. So now we'll pivot and talk how we're working to advance scientific software productivity and sustainability across this ecosystem and community. As we mentioned, ECP is a collaborative project across many labs, universities, and we're working in a way where aggregate teams are coming together to achieve new science advances. The diagram on the right is one way to think about these aggregate teams or teams of teams, where we have existing very successful groups who are now working together in these new ways. So the box on the bottom here shows some of the very important roles that we have throughout the community. And I would just like to draw attention to three in particular that are incredibly important and are really the glue that's enabling us to function so effectively now. One of those roles that we're using in software technology is that of the project coordinators, and the project coordinators are playing critical roles in helping us to focus on planning and integration across our community. We're also working with social scientists to help us more effectively collaborate with our aggregate teams. And of course, across all of our community, research software engineers are really doing the lion's share of the work of implementing important, challenging functionality and collaborating across disciplines and across teams. Here's just a quick shout out to a few research software engineers who happen to work at my institution, Argonne. But I will mention that we have many, many wonderful research software engineers who are working throughout the whole ECP project and, of course, in many projects throughout the world. So we all want to thank RSCs for what they're doing and work to support them. This slide shows the approach that's being taken by members of the Ideas Project, which is the cross-cutting project that's focusing on software productivity and sustainability issues. The approach here is for our team members to work throughout the ECP community to help teams identify and improve software practices that those teams decide on their own that are areas that may be worthwhile of focus and improvement. At the same time, we're working to establish software communities. We just talked about that through software development kits, and we're pursuing outreach in order to communicate with the broader computational science community. Here is just a snapshot of the many wonderful contributors in this project. They really are leaders in both the application space and the scientific software space, as well as leaders in facility computing. So we're grateful for all the work that they're doing. Here is just one example that is showing the impact of work in continually improving software practices. This is an example of work in a process called productivity and sustainability improvement planning. This work was led by Elsa Goncharovsky and Reid Milovich, collaborating with the HDF5 group, and they all work together in order to identify some bottlenecks and work to find ways to improve them, so that while making these improvements in documentation, repository management, and coding standards, while doing that, of course, HDF5 group was also still working to support many users who rely on their technologies, and at the same time enhancing their technologies to provide better functionality on new architectures. So a key element of this approach has been finding high impact elements of work that an individual team wants to work on and improve, and then defining key steps to make those improvements while still meeting their other science goals. There's some good links here to a presentation by Elena, Reid, and Elsa. I encourage you to take a look there and read about what they're doing. I would emphasize that this approach can apply to any project, no matter how small or how big. So it's really good food for thought. Outreach is a key element of work at the Ideas Project, and we're grateful that David Bernhold of Oak Ridge has been leading the outreach thrust of our project since inception. He and the rest of the tutorial team did a terrific tutorial here at Supercomputing a few days ago, and they continue to lead tutorials in other events. This is a great way for anyone who might be interested to go online. The slides and even some recordings are available. So there's ways to benefit even if you do not have a chance to attend in person. Another important element of outreach has been our webinar series led by Osni Marquez of Lawrence Berkeley Lab. This webinar series is a monthly sequence that focuses on best practices for software developers. So we encourage you to take a look and see. These are archived so that you could take a look at both slides and recordings, depending upon what your preference may be. Another element of outreach within the Ideas Project is organizing BOFs, such as one that took place yesterday. Very, very interesting and exciting, as well as organizing other events in the community. And I'll mention one event that took place just a few months ago is the Collegeville Workshop series on scientific software. There's some summaries of outcomes of that workshop. I encourage you to take a look. Last year's focus, this summer's focus, was on scientific software teams. Another element of endeavor within the Ideas Project has been communicating across diverse teams. We found that panel venues can be very, very informative and effective. And last year, Anshu Dubey from Argonne led a series focused on performance portability. So that's been a great way to advance dialogue about approaches that are underway in order to enable our community to learn from one another. And we're also excited about a panel series that Elaine Rayborn from Sandia, a social scientist, has been leading. This focuses on strategies for working remotely. And I encourage you to consider Tomorrow, there'll be a panel series here at Supercomputing focused on why we want to work toward sustainable approaches for hybrid environments where some people are remote and some people are on site. And in fact, if we think about how computational science and high performance computing works with collaboration across institutions, in fact, that's how we collaborate. And so it's a really important long-term element of focus for our world. I'll mention the Better Scientific Software site. This is an online site. It's an outreach element of the Ideas Project where we're trying to provide a venue for anyone in the international community to share their perspectives about software issues related to improving sustainability of software and improving the productivity of software developers. We encourage you to consider not only reading the material, but consider contributing. Rinku Gupta from Argonne is our editor-in-chief, and I'm sure she'd be glad to provide information to anyone who's interested. So I encourage you to sign up to receive email digests. We send information just once a month, so it's not a high volume email, but there's a lot of good material there. Another element of outreach is our Better Scientific Software Fellowship Program, led by Fellowship Coordinator Hea Nam of Berkeley and our new Deputy Coordinator Elsa Gonczarowski of Livermore. This slide shows the broad range of people and topics where the teams have been making advances in many areas that relate to improving software practices and culture in our community. I am incredibly excited to mention that the ECP recently established a task force who is working toward broadening participation in the ECP and high performance computing community generally across the DOE complex. This slide shows that we're working across multiple thrusts, 3 complementary thrusts of improving culture in our individual labs by sharing information about experiences and best practices. We're working on a new element of introductory accessible training for beginning people who do not have experience in high performance computing. And we're working toward an internship program that is providing sustainable pathways for people to begin research and development careers in HPC. We're grateful to be partnering with Marianne Lung in this work. Marianne is a longtime leader in our community, and she has established the Sustainable Research Pathways Program, which has been an effective partnership with Lawrence Berkeley Lab for a number of years. And we're really enthused to announce that beginning now, we're expanding that very successful program to incorporate collaboration across the ECP community, where we are now reaching out to encourage students from underrepresented groups and also faculty who are working with students from underrepresented groups to consider applying for this program. There's many more details that are available online through our website. I encourage people who may be interested to take a look at the website listed here. So key elements of what's special about this approach is that we are incorporating important work in community building and mentoring, as well as an iterative approach to refining the approach for a particular person or team's work in collaboration with the ECP community. So this is not intended to replace existing internship or workforce programs in the lab community or otherwise, but rather to supplement and complement it, leverage and take advantage of the special circumstance we have being a multi-lab, multi-institutional ECP community to work together on this problem. So in summary, I'll just wrap up by re-emphasizing that because of the complexities that we're facing in high-performance computational science, it's imperative that we think about ecosystem points of view very deliberately. In the past, I would say ecosystems naturally evolved because each one of us has been using software developed by others as we've done our work. But what's different and what's so challenging now is that our complexity is advanced to the point where we can't now just use whatever happens to evolve. We really need, as a community, to think about this from a more deliberate point of view. So I encourage each of us to think about what ecosystems we might want to use and be a part of, and just encourage people to consider the E4S endeavor, and also think about what endeavors might make sense for your needs. We're not trying to suggest that E4S may be the answer for everyone, but we do think that considering ecosystem points of view is very valuable, no matter what kind of software you're working on in high performance computing. So again, in summing up, there are a variety of organizations in the international community who are working very hard to address the many challenges of high performance, high quality software. We encourage you to investigate those and get involved, and really internalize the fact that investing in high quality software, better software for yourself and for teams who work with you, really does pay off in the long term, even though, of course, it requires some time to do initially. So let's just pause and think back to the initial exercise that we did at the beginning of this presentation, where we each thought about our relationships to scientific software. So bearing that in mind, I challenge all of us to really think about how we, as members of the HPC community, could make progress going forward, changing our expectations and behavior. So for those of you who develop and use HPC software, I think it would be really wonderful to very deliberately think about what your bottlenecks might be in your project. Talk with your team members and advocate for change and lead change in your projects. And when you do that, then also share your insights. Consider contributing blog articles or other ways of communicating outward. And also check out community activities such as the Research Software Engineering movement, where there are a variety of international opportunities. Also, if you lead projects or organizations where teams are developing software, think carefully how you as a leader of those projects or organization have a role to play too in continuing to emphasize the importance of ongoing software quality improvement, and also providing clear and sustainable career paths and mentoring for software professionals, especially people who might be working in scientific software as research software engineers. If you're a stakeholder or supporter of projects, I believe it's important to consider incorporating expectations of high quality software and sustainability, and consider how to incorporate funding for that work, as well as to incorporate expectations for transparency and reproducibility. And finally, I would say that all of us have vested interest and opportunities to work on changing culture. And that includes things like changing citation credit models, incentive metrics, education, training. They're difficult long-term challenges, but we each can take actionable steps to help improve. And I'll leave with just a few comments about some ongoing opportunities for input to some town hall meetings. In fact, there's one taking place tomorrow where we're looking toward leadership scientific software opportunities and challenges. Also, there's an upcoming workshop that's focusing on the research of scientific software. And I'm sure many of you have already noticed there are lots of great events at Supercomputing related to software, so I encourage you to check them out and get involved. And that is all. The slides have a few more references here, but we do not need to dwell on those. You can just check them out if you want to look at the PDF file of the slides. Thanks so much.